Hello YouTube! Today we're going to be talking about springs. In particular, we're going to be talking about how much force they put on stuff, as well as how to figure out how much energy will be stored up in a compressed or stretched spring. That's pretty much it. Let's get rolling. So, big idea is to be able to use concepts of work and energy to model motion, except now we're going to be doing it with springs involved. So it's honestly going to be the exact same as everything we've done before, but there's sort of one extra thing that can be in the equation. In particular, you should hopefully be able to model the force on an object from a spring, as well as model the potential energy that's stored in a spring from, again, the spring being stretched or compressed. So, I didn't forget to write the equation on this sheet. You forgot to write the equation on this sheet. Springs work such that if you take a spring and you pull it back, the further you pull it back, the harder it tries to pull you towards the middle. And this leads to an equation where for an ideal spring, which is linear, the force from that spring will be equal to negative kx, where k is the spring constant of that spring measured in newtons per meter. It's literally just telling you how hard the spring pulls back every time you stretch the spring out by a meter, which is quite far to stretch a spring. And x is telling you how far you've moved the spring away from where there's no force. So springs, if they're just kind of sitting there, will have this ideal state that they want to return to, because metal has sort of a memory of its original state or original shape. And so once it's locked into that shape, if you pull it back, it'll try to get back to that shape. So if you push it forward, it'll get pulled backwards. If you push it backwards, it'll get pushed forwards. And that's why that negative is in that equation, to just sort of make it so that the force will be a restorative force trying to pull the thing that's on the spring back to the center by the amount from Hooke's law. So let's do a quick example. A 0.5 kilogram block is put on a vertical spring with a spring constant of 50 newtons per meter and gently lowered until it does not move when let go. How far down does the block go? So the basic idea with this one is we've got this spring system, and when it's not stretched out, we're here. When it is stretched out, we're here, which is some height down. And at this point, it doesn't move when we let go. Up here, it would. Now at this point, the force from the spring is equal to 0 because we haven't stretched it at all. Whereas at this point, the force from the spring will be equal to negative, meaning, well, we'll get to that, negative k times negative h, because if we're defining down to be negative, the spring is pulling it. If we're defining down to be negative, then our displacement from the center is going to be negative h. We'll have a negative displacement because we have because we are in the downward direction from where we started. We know that k equals 50 and mass of the spring is 0.5. Okay, great. So, how far does the block go? Well, basically we just have one quick concept here, which is that if we think about the forces acting on this thing, if it's not moving when we let go of it, those are the points at which the force is balanced. If we take the spring and we pull it further, because we've got that negative kx, the further we pull it, the bigger the force going up will be. But the force going down will always be mg. And so what'll happen here is we'll have this setup where, sorry, I just started thinking about the next thing, which would be talking about how to put this on a graph to, my bad. So we've got the situation where the more it gets pulled up, the more force we have going against gravity, and that happens the lower down it gets. The sweet spot when it won't move when we let go of it is when those two things are balanced out with each other. And so what we can say is that because our net force in the y direction is going to be equal to negative k negative h, this right here, plus mg, or I guess minus mg going down, and that will need to equal 0. It's a fairly straightforward problem if we're solving for h and everything else is given. Add mg to both sides, add mg to both sides, and we'll get that kh, our two negatives have canceled, is equal to mg. Divide each side by k, divide each side by k, and we're good to go. The height at which it stops sort of doing the thing is mg over k, which is 0.5 times 10 divided by 50, which is 1 over 10, so 0.1 meters. Cool. So that's it. I do briefly want to talk about something weird. Because gravity is a fixed force and the force from a spring increases linearly. When you're thinking about a spring from a perspective of force, what winds up happening is that if you graph it, the force from your spring will look something like this, where the further you stretch it to the left, the more it'll get pulled to the right positively. The further you stretch it to the right, the more it'll get pulled to the left negatively. And if you look at the net force from the force of a spring minus mg, because this is a fixed value, it'll just be taking this thing and dropping it down. And so you'll wind up with a new linear function such that when the spring is at negative h, the one we just found of mg over k, finding your x-intercept using your y-intercept of mg and your slope of k, and actually that's actually probably pretty relevant. This is our y-intercept. Like if we look at this equation, this is our y-axis, this is our x-axis. So our intercept in slope-intercept form will be negative mg. So our y-intercept will be here. Our x-intercept will be mg over k. And it'll still be a linear function. And so we could sort of reconceptualize things so that if we shift our x-axis over to think of our new x-axis or new origin to be at mg over k, basically the point at which it's at rest if you let it go, then that actually functions like a new equilibrium position. And it's such that if you move past that, it'll get restored back to the middle, and if you move below, it'll get restored back to the middle just by the same amount as if it was shifted over and looked like the normal graph. So when we do eventually get to what happens when you like pull a spring back a little bit and let it go and it sort of goes back and forth for a really long time, the reason why you can basically treat a situation where a spring is being pulled by both a spring and gravity like the 0 point is the place where there's a net force of 0 when the gravity and spring are balanced with each other, is because of this thing with the linear function where you can basically reset your 0. A little not what we're talking about right now and a little further than we would need to go, but I figured it made sense to talk about it while we did this problem where it was directly relevant, or could become directly relevant. All right. So next up is the potential energy from a spring. And that's actually pretty easy to derive because work is equal to the integral of force as a function of position with respect to position. And what that means for a spring is that it'll be equal to the integral of negative kx. Now, one thing that we do have to be a little bit dx. One thing that we do have to be a little careful about is that this will be telling us the kinetic energy that the spring will give the object if the spring pushes it from the start location to the end location. And we should pick the start location as the center of the spring. And so we should actually pick the start location to be the place the furthest out from the spring, and the end location to be the center of the spring. And what that'll do if we set it up like that is it'll tell us how much kinetic energy we would gain by letting the thing attached to the spring go and letting the spring do its thing. And so when we do that and we take that integral, it's fairly straightforward because it's just a polynomial. We'll get negative kx squared over 2, so I'm actually going to go ahead and pop in a negative 1/2 kx squared, and we're evaluating it from x to 0. And so when we plug in those values and do our evaluation, we'll get 0 minus negative 1/2 kx squared. And what that tells us is that when we stretch a spring back, the energy that the spring will be able to give the thing if we let it go, kind of sounding like gravity and potential energy, is going to be 1/2 kx squared. Well, that means that we can just say this is potential energy. And we'll get a little bit more into why we can say this is potential energy. There is actually a special set of conditions for that, and we'll talk about it next time. But this is the potential energy stored in a spring, because if you let that spring go, it will always give this much kinetic energy to the object. This specific equation only works for ideal springs. If you have a non-ideal spring, you would have to rederive it like this. You'd have to take the force equation and take your integral. And that could actually come up on the AP exam, so just, I guess, be careful about that. But hopefully this process was simple enough that you'd be familiar with the idea that you can just take the integral, find the work, and that work will be equal to the amount of energy stored by the thing. I'm actually going to go ahead and take a screenshot of this real quick, because that means that I can add this to the notes after today. Oh, don't have to, because we've got this. So this is the potential energy from a spring, and there's our equation. EUS is equal to 1/2 kx squared, where k and x are the same as they were previously, and EUS is potential energy, which one? The energy from a spring. So E, energy, U, potential, and then the subscript of U is which potential energy? Spring potential energy. And so what you can do is take problems like ones we were doing before, where you like launch a block, or you have a situation where something's moving between a few different locations, and you can very easily figure out about velocities or heights or compressions now from a spring, because you know ways to relate them using energy. Oh, that was exciting. I should have probably muted. So doing this problem, we've got a spring with a spring constant of 400 Newton meters, and we've pushed it back by 0.5 meters. Unfortunately, I am going to start having to give you masses for stuff. So this is a, you know what, I'm actually going to make it a 2 kilogram block. I just realized that a 10 kilogram block might be going a bit too slowly, because 10 kilograms is a lot. So a 2 kilogram block gets launched across a surface with a coefficient of kinetic friction of 0.2. Slides for 3 meters after that. So we've got x1 is this, x2 is 3 meters, before it goes off a frictionless ramp, launching it at a 37-degree angle, then goes up, and we want to figure out how high it is at this point. Wonderful. Oops, wonderful. So, them's our givens. The one thing that I want to be careful about is that, in particular, is that if I'm looking at this, I might be tempted to be like, okay, well, a lot of times the way that energy works is we pick sort of two locations. Location 1, and I'm going to go ahead and label this one location 3 as a spoiler, but and we have our two locations. And we can pretty much ignore everything that's happening in the middle as long as we're careful about keeping track of any work that happens in the middle. And the only work that's happening is from this spring, which I can track with potential energy, and from friction across this entire distance. So it'd be tempting to just be like, okay, well, energy here, done. The one reason I don't want to do that is because if I were to do that, up at this point, we have both potential because it's going to be at a height, and we're going to have kinetic energy because and potential from gravity, and we're going to have kinetic energy because it's going to still be moving sideways. So if I want to find the height, I'm going to need to know how much kinetic energy it has so I can figure out how much is left for potential. So I'm going to need to know the velocity of this thing. But the velocity of this thing is going to be based off of Vx, or proportional to Vx. So I'm going to need to know what Vx at the time of launch is. So I'm actually going to need to care about the launch. So what I'm going to do for this one is I'm going to figure out how fast it's going at the launch point. Once I know how fast it's going at the launch point, it's pretty easy to just say that the energy from the launch point is equal to the energy at the top because nothing's doing work after that point. So what I can do is say that at location 1, so I can do the energy for location 1 to location 2. And for that, what we've got is 1/2 kx squared plus the work that's done by friction, and that'll need to equal 1/2 mv squared at location 2, so 1/2 mv2 squared. And then once I've got that, then I can use the energy from location 2 to location 3, which thankfully has no work involved, so I can say that 1/2 mv2 squared will be equal to 1/2 mv3 squared plus mgh, where V3 is equal to the x component of velocity 2, which because of the 37-degree angle, I can say that the x component of V2 is going to be V2 times the cosine of theta. Great. So let's figure out what V2 is using this stuff, and then bring that over here in those two spots, and our only variable will be our height. So we've used friction quite a lot at this point. Our force of friction is going to be equal to our normal force, which will be balanced out with gravity. Our normal force times mu, so our force of friction is going to be mu times mg. The work that's done is going to be negative because it's going to be going backwards. And we're going to have mu mg times our distance, which is going to be x1 plus x2. And that will need to be equal to 1/2 mv2 squared. If we're looking for v2, we have to divide by 2, multiply by 2, divide by m. And then we're going to have to square root. And what that'll look like is the square root of k over m times x1 plus or minus 2 mu g x1 plus x2. And that'll be V2. I don't normally do this, but especially for the ones with springs and like just so many moving parts, it probably makes sense to just get our number here. So I don't have to write all this when I plug in for V2, which I'm going to have to do in a couple different places. Seems easier to just hold off. The other thing we could do is prep by solving this one until we've got it solved for H and then going from there. I'm actually going to do that. Okay. So at this point, I know V2, I just have to plug in numbers. I'm going to get this one ready so I don't have to work with all of this when I plug in V2. I can get it solved for V2 in the right spots and then slot this in afterwards. To do that, I am going to have to slot in my V2 cosine theta instead of V3. So we'll have 1/2 m V2 squared equals 1/2 m V2 cosine theta squared squared. Cosine theta squared plus mgh. I need to get rid of 1/2 m V2 squared cosine theta squared. 1/2 m V2 squared cosine theta squared. That'll give us 1/2 m V2 squared times, if I'm factoring out the 1/2 m V2 squared, 1 minus cosine squared theta equals mgh. If you've got your trig functions memorized, you might recognize, I'm crossing out the m's, you might recognize this, and divided by g. You might recognize 1 minus cosine squared theta as sine squared theta. So that means that our final answer, if we want to simplify a bit, will be 1/2 V2 squared sine theta squared over g equals h. And now I can just slot this in and be good to go. So 1/2 root k over m x1 minus 2 mu g x1 minus plus x2 divided by g times the sine squared of theta equals our height. Putting in all our numbers, we've got 1/2 times 400 over 2 times, squared, squared, squared. Almost dropped that. That would have been bad. 0.5 squared minus 2 times 0.2 times 10 times 0.5 plus 3. All of that's to the half because it's square rooted, divided by 10. Which I should grab my calculator and find, I suppose. We've got 1 divided by 2, parentheses, 400 times, well, I guess actually it's going to be just divided by 8, because 0.5 squared is 1/4. Minus 2 times 0.2 times 10, which I guess it could have just been 4, times 3.5. All of that is getting square rooted and then divided by 10. 0.3. So 0.3 meters is our final answer. And very glad I changed the mass. I'm pretty sure that if I hadn't, we would have wound up with a impossible answer because we would have had to square root a negative. So, taking stock of all that again, because I want to make sure we're going through the steps for the problem. We were able to use the work and energy, the energy stored in the spring, minus the work that friction took away from the spring to figure out how fast it was going at launch. Once we knew how fast it was going at launch, we were able to use the kinetic energy it had at launch and set that equal to the kinetic plus potential energy it would have at the top. In particular, finding the launch velocity because the velocity at the top was related to launch velocity by being the x component of the launch velocity using the angle from launch angle. And going through and doing all the math out, plugging all that in, this is where we got. I think I caught all of the things I might have missed, but honestly, it was a fairly long problem, so if you notice anything, let me know. Hope you have a great day, and goodbye, YouTube.